A very good afternoon to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering from the Institute of Aeronautical Engineering. I'll be dealing the subject robotics, and my today's topic is Euler Formulation. Right? What do we mean by the Euler's formulation? What is the use of this particular formulation? Right? In the earlier class, we have discussed about Euler formulation, but we have not come across what is Newton's Euler formulation and what is the use of that particular Newton's Euler's formulation. Right? So that we will be discussing today. Generally, this combines the Newton's second law of motion, right? This particular Newton-Euler formulation is the combination of Newton's second law of motion along with the Euler's equation, right? It is the combination of Newton's second law of motion along with the Euler's equation in order to get a rotational motion to the with respect to the force and torque. Right? With respect to the force and torque, we will be getting a rotational motion with the combination of Newton's second law of motion and the Euler's formulation. So this particular method is used to calculate the dynamic equations, right? Such as in order to have the essential tasks like control or simulation or motion planning. Whenever we come across this particular type of the concepts, we need to add Newton's Euler's formulation, right, for easy movement or for easy dynamics. That is, generally this particular type of fundamental approach is used for the dynamics of the robot system for rigid body mechanism. Generally, when we have the context of rigid body mechanism, we come across the Newton's Euler's formulation, right? So here, as per the Newton's law is sigma F is the force is equal to ma, right? Sigma F is equal to ma. That is, the force acting on a body is equal to the rate of change in its linear movement, right? The force acting on a body is equal to the rate of change of its linear momentum. So sigma F is equal to m into a. Now in this, where F is nothing but the sum of the external force, we all know m is nothing but the mass, a is the linear acceleration of the body center, and as per the Euler's equation, we write the Euler's equation as sigma tau is equal to sigma tau is equal to dl by dt, which is nothing but I alpha plus omega into I omega. So this is the equation for Euler's equation for a rotational motion, right, which is the sum of torques. It states that the sum of torques is equal to the rate of change of angular momentum, right? The Euler's equation states that the sum of torque is equal to the rate of change of angular momentum, where T is the external torque, L is the angular momentum, I is the inertial tension, and alpha is the angular acceleration, and omega is the angular velocity, as we all know. So this is about the combination of Euler's as well as Newton's equation. So when we come across the application where exactly this particular formulation is being required, right, that we need to know. So generally, when we have the robot when we need the robot to be moved in the forward direction, or when we need to have the movement of the robot in the dynamic strain, this forward kinematics, or when we need to come across the dynamic equations, this particular Newton-Euler formulation is very important. That is, it is applied for each and every link of the robot manipulator, right? This particular sort of the formulation is applied to each and every link when we come across for each and every link. We are applying this particular Newton-Euler's formulation to get where the robot manipulator is used to derive the equation of the motion, right? So in the forward calculation, we will be calculating the position, right? In the forward calculation, in the forward kinematics, we will be calculating the position of the robot. We will be calculating the position of the robot. We will be calculating the velocity as well as the acceleration. Velocity as well as the acceleration of the robot. When we come across the dynamic equation is used for the translation equation of each link, or for the rotational equation for each link. Right? So when we come across the dynamic equation, it is used for rotational equation as well as it is used for the translation equation for each and every ring. That is rotational as well as translation. Rotation as well as translation. Right? And the third one is recursive computation. That is, most of you are not aware what this particular recursive translation is. So this is related to the root link or the last or the backward recursion. When we have a forward recursion or when we have a backward recursion, this comes into action. That is, when we start from the base of the robot and move outwards to the force and the torque of each link, this particular recursion computation comes into account. That is, when we start from the end effector, which is used for propagating the torque and the force. Right? When we start from the end effector, which is used for propagating force and torque, back to the base, right? Back to its particular recursion. That is known as recursion computation. Let us take one example. How can we explain this particular Euler's formulation with the help of the two-link robot manipulators, right? Let us take a small example. So when we are considering a two-link robot manipulator with respect to the Euler formulation, first we need to apply Newton's law. The first step is to apply Newton's law. What is Newton's law? Sigma F is equal to m into A. Right? First we need to apply the Newton's law. Then we need to apply the Euler's equation. Right? Then we need to apply the Euler's equation, and then we need to combine both this Newton plus the Euler's equation. Right? When we are doing in this particular procedure only, we will be getting a two-link robot manipulator. Right? So here we have few advantages when we use this Newton-Euler formulation. So what are the advantages? That is nothing but efficiency. Efficiency is one of the main important constraints which we need to follow, or versatility, or foundation for the control. Right? Efficiency means what? Why is efficiency coming into one of the advantage or one of the use? That is, when we have the recursive nature of the Newton-Euler formulation coming across the computationally efficient real-time control of the robot, efficiency plays a very important role. Or when we come across the complex multi-body system, the versatility plays a very important role. Or when we come across the dynamic equations, or when we come across the adaptive control or advanced implementations, the foundation for the control plays a very important role. So this formulation is generally plays a very crucial role in design, analysis and control of the robot system. Right? Next, coming to the comparison. How do we compare this particular Euler and the Euler formulation? How can we compare this particular two formulations? That is, generally when we come across this type of formulations, both these fundamental approaches in the field of rigid body dynamics or in the field of mechanical system, it plays a very vital role. That is, as it serves different purpose with a distinct contents. Right? This when we are combining this Newton-Euler's and Euler formulation are both the very fundamental approaches in the field of rigid body dynamics. Right? And when we come across Newton-Euler's formulation, here Newton-Euler formulation is used to drive the equation of motion for a rigid body, as we have already discussed. Right? Whereas Euler's equation is used for rotation, that is in order to find the force and torque acting on the rigid body. Right? So what is this Euler formulation? Generally, the Euler's formulation specifically refers to the equation of motion or the rotational dynamics of the rigid body. Or when we come across the different relation between the torque or angular movement, when we come across the relation between torque or the angular movement or the rotational matrix, without directly addressing the translation matrix, right, or the translation motion, without directly addressing this particular translation motion, the Euler's formula is being used, specifically refers, right? Or when we come across the primary uses or the use of importance of rotational dynamics, which are interests such as spinning bodies or gyroscope, or for rotating spacecraft, the Euler's formulation is very important, right? Or when we come across involving the rigid body rotation, or when we come across the calculation of the rotational dynamics of individual linking arm, the Euler's formulation plays a very important role, right? The Newton-Euler formulation is the method which is used for analyzing both the translation motion as well as the rotational motion, right? So Newton-Euler formulation is a method which is used to analyze the dynamics of both the motion, that is whether it is a translation motion or whether it is a rotational motion for the robot manipulator, right? So in order to study the rotational dynamics, or in order to have the essence of the context for the rotational motion, this is a primary concern, right? The Newton-Euler formulation is one of the primary concern when we need to study the rotational or the dynamic movement of the robot, right? So these are the references which we have gone through, right? So what is the Newton-Euler formulation? It is nothing but the combination of the Newton's second law added up with the Euler's formulation, that is the Euler's equation. What is the Euler's equation? This is the particular Euler's equation, that is dl by dt, that is nothing but I alpha plus omega into I omega, right? So when we are combining both this particular Newton's formulation and Euler's formulation, we will come across describing both the rotational as well as the translational motion of the robot which is being designed, where we take T as the torque, where we consider torque, force, angular velocity, right, acceleration, gravity, force, mass, area, all these come under considerations, right? So hope you have understood about Newton-Euler's formulation. So this is all for today. Signing off for today, Dr. G. Hima Bindu. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.